My name is Rodrigo Gonzalez. I am the head of robotics at the Construct. Today, I'm going to talk about our journey with Zenoh. More specifically, how we use Zenoh in our products in order to ensure fast and lightweight connectivity for all our robots. We are the largest online robotics academy in the world, and we provide tools and resources for learning and developing robotic skills and programming. And as the head of robotics in the Construct, I am in charge of developing and maintaining cloud-enabled solutions for our students to practice and develop their algorithms in real robots. And let me show you a video from our robot cafeteria, which uses Zenoh and is my example today. So as you saw, there's a lot of robots in play here. So coordination between all robots is required and expected. This can be done with a single robot with a default off-the-shelf humble ROS2 humble DDS configuration. However, with more than one robot, especially as you expand, the default DDS implementation, the setup off the shelf with ROS2 humble is impossible. It's just very, very hard to make it to work and have every robot discover each other robot easily and quick and reliably. And Zenoh provides the solution for this problem. I first want to mention the main problem that happens with a default multicast DDS discovery setup. So on the right here, you can see an image of a router traffic monitor or router with a huge spike on the right, a blue spike of traffic that happens when we launch all the nodes that are needed for this system to work. So that's a huge number. That's like 2 gigabytes per second, which of course causes everything to crash down and connections to drop. This is the solution, or a diagram of the solution we implemented with Zenoh. After this solution, we can take a look at our issues after Zenoh, which are none. The student at their laptop can connect to our platform and then connect to our real robots, all with the help of Zenoh, and there are no issues with communications, no drops of messages, nothing like that. So I'm not a networking expert, but this is exactly what I'm looking for a solution, is to just run a couple of things that make the middleware invisible, so I won't have to worry about it. Is that in my experience, Zenoh provides the best solution to connect multiple ROS2 robots.
Hello, welcome all to my presentation about Zenoh on PX4 for multicast distributed networking between PX4 and ROS2 nodes. I think it's lots of jargon, but mostly we've been using Zenoh Pico specifically for PX4 autopilots to communicate with also bigger system ROS2 based systems. So very rough introduction on PX4 middleware. So PX4 typically is a FMU, which is a flight management unit. So that's a microcontroller that takes care of all the sensors, actuation, and tries to stabilize the drone. It runs the NUDX operating system, which is a small RTOS. And then internally, we have this MIORP to have all these sensors, attitude control, RC input. And roughly introduction to Zenoh. So the nice part, what we liked about it, it scales from big systems to small systems, and also the fact that it supports different wire formats. So we still have systems where you might have to use serial, USB serial, Bluetooth. So even the things where we're looking at, we see that, hey, it's very extensible. And from the end user, we like the concept, okay, well, you can do this publish subscribe through this API on the high level, and then everything beneath it should take care of it. Well, should take care of it. That's the goal you have in mind, and I think Zenoh does a very good job, also with the router, and has worked it out nicely. Um, so yeah, we come to the router part. So typically we are interested into P2P communication, but even the brokered and the meshing network is still very interesting for us as well. If we think about different setups, so if we think about a combined system, we could have multiple vehicles through routers. We could have a ground control station. That's the terminology they use for drones. So you're flying your system, you're on the ground, you have a 4G uplink, or you have other links. And the nice part, you can use Zenoh to route the data back to you to get real-time status of your vehicle. And if 4G, you can also bring that into cloud. So what you see that even if you think about the nice topology image of Zenoh, it really pairs nicely to multiple robotics system where you can have interconnection and have all these fleet control, and we can use one protocol for that. So that's really a concept we want to use. But mostly we just started with Zenoh to ROS2 bridging. So we have ported Zenoh to DPX for autopilot. We have a router running on a Linux system, and then we use the DDS bridge to bridge it with ROS2 nodes. So how does that look like? Well, so this is the kind of architecture we are interested in, to think about redundancy. So we could have a flight controller, but even a second flight controller, but then you have to synchronize those states. And if you think about autonomy, you want to also add a companion system. So what we typically would have, if you have DDS_XRC as an agent or some kind of auto protocol MQTT, you always have to send from system 1 to system 2 to system 3. But the nice part about Zenoh is that it's implementing multicasting. So the switch can already duplicate the packet for you. Especially on small systems, this is important because we just want to send a single packet, and it's kind of like fire forget for that. So we don't need a broker. The switch takes care of it for you. So this is a demonstration of that. So in the center we have the switch. We have one system that takes the remote control input. We send it to the switch. The switch acts as a multicast system. And then we have two systems controlling the speed controller. And then we have a nice visualization on how the motor should turn. Okay, yes, now the picture is working. So we are sending speed commands, we do the steering actuation. And what we now show is that either this canvas can fill, so we have it in the canvas, so we can just take out the canvas, but the system still operates because it takes in the same actuation command from the user. So it's a nice example where we can think about redundant networking setups. So for now in PX4, we have implemented Zenoh Pico. It's still based on the old 0.7.0 functionality. I'm trying to work on the newest Zenoh release, Dragonite. Well, also exciting about the Zenoh alternative RMW. So hopefully we can even do some experiments without using the router DDS bridge, just having a basic implementation. And yeah, cloud control, cloud communication through Zenoh. I think this is a very unexplored area, and I think there's some opportunity there. And also, I'm curious if people are interested in here as well. So I just put it here. It's kind of like this unification of Ethernet campus through Zenoh. So can we also maybe, like Zenoh is quite versatile. You can use it on serial TCP UDP. Could you also use it on Canvas and even use Canvas networking for very small sensors? Like you have these voltage sensors or small buttons like a safety button. can you utilize Canvas for that and then still bring that into Zenoh and into the ROS or into other system where you can think fail-safe mechanism, but then from the end user, they can just use one same framework.
I'm Nazmi from Filics. When you rethink the forklift, we want to make this process somehow automated, flexible, and more intelligent. So with the big forklifts, you have to go in there one by one and then take everything in. But here, maybe you get a glimpse of our robots working together. This is our vision, where they bring the pairs of robots, bring the new pallets, and then they automatically go inside the truck. And then they just leave basically because they are so minimalistic and they can leave through between the pallets. But why do we use Zenoh? We were using native GTS, and this is actually not really scalable. And when we go do pilots in the warehouses, the network quality is especially bad. And for this, we have to introduce some sort of different way to distribute the topics that we need for our robots to run reliably, basically. And as Rodrigo before me explained, this is costing a lot of, in terms of CPU and networking, a lot of energy to you. That's why we wanted to move with Zenoh and then highly optimize what we want to distribute between and actually just get rid of this overhead of discovery traffic.
So hello everyone, thanks all for joining in this occasion. I'm glad to be presenting along with Yaru about some work that's been going on for several months now. This work lives within the ROS2 ecosystem and is focused on a new implementation of the ROS middleware. ROS is the most widely used open source development kit for robotics, and it's definitely a tool worth to be checked out if you haven't. The reasons we embark on developing a new alternative middleware are related first to the fact that when using DDS, it generally requires some careful tuning to match your use case, and this makes ROS2 probably not being as pleasant as out-of-the-box experience. For example, you might find some failures from UDP multicast in DDS, some discovery failures due to scaling issues of the UDP multicast. The multicast service isn't always allowing routers or large Wi-Fi networks. Also, difficulties transferring large payloads. This is typically problematic in Wi-Fi networks where the connection might be unreliable. So we gather requirements via several sources. There are some known ROS2 use cases that we use as baseline. Also via targeted interviews with key stakeholders in the ROS community who share many insights from their use case. And we also sent out a survey to the ROS2 community. We got almost 200 responses, which helped a lot to understand the user and identify requirements.
So we took all those requirements and then we also came up with a list of middlewares we want to evaluate. And these list of middlewares come from that user survey we conducted, but also some insights that we have into the industry and as well as some other protocols that we wanted to try. But I just want to highlight right now of how Zenoh did across all these other middlewares. As you can see in the slide that's highlighted, the column in red, that's the entry for Zenoh. And you can see a lot more green than red. So that should be an immediate indicator that Zenoh fared really well against our evaluations. So across all of these different middlewares that we evaluated, Zenoh definitely stood out to us the most. From the results of the user survey, if we rank what were the popular middleware suggestions from the community, Zenoh was number one. So it's great to see that we kind of independently arrived at this conclusion, both from our systematic study as well as a popular vote from the community that Zenoh should be the next middleware that we rely on for ROS2. So RMW Zenoh is the ROS2 middleware package that we're writing that's based on Zenoh. And it's a C++ package that relies on the Zenoh C bindings to implement certain interfaces defined in the RMW package. So we want to make it such that users can just change a single environment variable that says, use Zenoh as my middleware, and then boom, all the nodes are communicating over Zenoh. And that's what this package does here. So the great part about Zenoh is it works in so many different topologies and it's different network configurations. we chose something that we felt would work across various robotics use cases and is simple enough for people to use out of the box or with minimal configuration if needed.
Stephen from GM connecting out of Canada. And so thank you again, Yadu and Franco.
I think this is actually a phenomenal segue because we're doing that same initiative that they did for us, coming to the same conclusions, working on the same integration, and actually learning about that pull request number 189 and 191 is going to address some of the questions that I have in some of our chat channels. So this is
okay, great.
This is good because we have that same gap trying to map it to what I'm going to talk about next. So,
yeah.
What I'm actually going to talk about today, first, before I dive into what we're actually contributing to the open source, is talking about GM's now embracing of open source, which is kind of a shift in mindset from what like Sarah was mentioning, something that historically we would pay large companies to build software that would be put into hardware components that would not be changed over time. Now we're talking about adopting open source, and not only adopting open source, but actually contributing to open source and learning from the community as we go. So then it comes to why Zenoh, which is very interesting, the previous presentation as well, because we're coming to the same realization that, well, actually Zenoh implements very well a lot of the concepts, a lot of the ideas, and a lot of the optimized the concepts and technologies that we want to do with uProtocol. It provides this lightweight, very efficient pub/sub solution, pluggable architecture, so we can plug it into others as we need it. So by that I mean, if you go to the Eclipse project and look at uProtocol, we talk about these bridges that are at the edge of the different devices. And from here, what we can do is that maps very well to the Zenoh router concept. And then from that, it's easier for our developers to say, oh, I can create a Zenoh implementation of this for this use case or that use case and so on. And so what we've done, rather than just from one OEM to a supplier and let's just behind closed doors, write a check and talk to each other close, we're going with the open approach to bring the community and the open source along with us. So we have now open sessions that I'll talk about in the last slide, where we are working with ZettaScale, working with the authors of Zenoh to allow it to meet the requirements that we have in the automotive space for safety, security, robustness, quality. So we're working with the community to bridge that gap, to provide a Zenoh solution for uProtocol, just like there was a Zenoh solution for the ROS, which was very interesting. I also have to say as a closing remark, it's a very pleasant engagement working with ZettaScale, very different from working with other companies, I have to say. We have done so much in the open in our current engagement, so it's and full of extremely smart people. So
thank you for the nice word on ZettaScale. Thank you very much.
I'm Elias de Coninck. I'm the senior robotics engineer of Tractonomy Robotics, and we're based in Belgium, in the city of Ghent. And we're actually designing and making AMR, an automotive mobile robot. So first up, let me introduce our robot. We actually call him the Autonomous Towing Robot 2 because it's the second one we have. This is pulling actually 600 to 700 kilograms with our base model and we believe up to 2000 kilograms with our newest and latest version. What we are doing is actually towing everything on wheels. So when you can attach a gripper to it and it has wheels, we can actually tow it. Like a lot of presentations shown before me, in the beginning, ROS2 had issues with scaling. So during this project, we actually tried scaling from one virtual robot to 200 robots, but we got already stuck at 40. And in that time, every robot, in our case, had roughly 10 nodes. If we would adapt this to our current robot, currently we have over 50 nodes for our single robot. So as in that state of ROS2, we wouldn't even be able to run our single robot connected to one of the other sites. Like, okay, our site was not local. It was running through a VPN over to a European center. I think it was located in Spain. So there was some distance, but we found out that even just the local Wi-Fi network was causing a lot of issues. What we did with this tool is actually test different RMWs. Initially, when we were using dashing during this report itself, the default version was FastDDS. And we saw that FastDDS was actually a lot worse in performance at that time than, for example, Cyclone. Cyclone would scale a lot better with more nodes. The discovery process was working a lot better. But still, we were hitting limits like once you reach 40, 50, 60 nodes. Then again, what is also very important for us is the latency of these messages. If you want to control your robot to a TL operation, you don't want to have a latency of 200 milliseconds. Or if it's really that it's a consistent 200 milliseconds, you can handle it. But as you see on the right bottom picture, it's actually fluctuating very a lot between different runs. So it was not consistent and we could not make it work. So we started looking for a solution, and that's also when we came across some nice guys from ZettaScale currently. So eventually the solution actually was Zenoh. We started using the Zenoh DDS bridge early or mid 2021. I believe so. It was a very early version of it. Bleeding edge. Yes, we were even using the master version of it. So we didn't even see the tagged versions yet. But at that time, we could already operate just the default stuff. Just pops up like the topic, subscribing to it, see information. And we started using it for getting heartbeat messages to our infrastructure, seeing where the position of our robots are, and all those kind of things. So eventually the goal was to adapt that early architecture that we designed into this concept. And we actually exploded the use of it by including multiple Zenoh routers in each site of a customer. And then for each customer, they would aggregate their sites and then have multiple customers. So we aggregate those again. And then you have in our cloud also a Zenoh router, which connects directly to the robots. And we can route everything to Zenoh. What helped a lot by using Zenoh here is the plugins. Because we can actually scale and adapt our own knowledge of Zenoh stepwise. We first started adapting our robots themselves. It was just plug and play. Everything worked out of the box. And then now that we can think of improving the performance once we go to the cloud, we can start removing ROS plugins on the cloud side to the Zenoh API. So this helps us in a good way because now you can actually also monitor each robot individually from anywhere in the world if you connect to our cloud infrastructure directly to the Zenoh router running in the cloud. But we can still, if you have access to the subnet, directly connect to the robot if you want to have more access to it.